You're listening to Medex, the Medical Extrusion Podcast. Presented by U.S. Extruders. Extrude with confidence. Custom extrusion equipment designed for you and your application.
Welcome to the Medex Podcast. I'm Steve Maxson. Today's discussion is focused on silicone medical extrusion, and our guest is Paul Mazelin, CEO of Simedex, based in Paso Robles, California. Simedex is a ISO 13485 certified company that extrudes precision medical tubing for medical device applications. Paul, welcome to the Medex Podcast.
Thank you, Steve. I'm flattered to have the opportunity to speak with you today.
Excellent. Paul, to start off, please give our listeners your background and the story behind Simedex.
Well, to really answer that question for you, Steve, I have to go quite a ways back. I was introduced to the medical silicone marketplace by my dad. During my childhood, he worked for Dacron, selling silicone implantable breast implants as well as finger joints. And this led my dad down the path to discover opportunities in the contract manufacturing space. He joined forces with a couple of his colleagues from Dacron and started a business called Specialty Silicone Fabricators. I ended up joining that company and worked there for 24 years prior to that business being sold. And the sale of SSF, as most people referred to that company, provided me the opportunity to then collaborate with some of my former colleagues to launch Simedex 5 years ago.
Excellent.
I will go on and say,
sure.
The answer to why to get the business started, simply it's fun. I enjoy participating in the technology and the problem solving that occurs in our industry and working with our customers. But ultimately, to know that we are impacting the standard and quality of people's lives in the healthcare segment is really what motivated us to launch Simedex. And the how behind it is by having good financial partners with whom we can borrow the necessary money to build out the clean rooms and buy the necessary metrology equipment that the industry demands at this stage.
From a quality standpoint, for sure. Paul, when you look at the market for silicone extrusions in medtech, give us a breakdown, if you can, of the difference in extrusions, medical silicone extrusions used for fluid handling applications for pharma, bioprocessing, peristaltic pump segments, to silicone extrusion used in catheters for class 2 short-term implantable devices, and then 3, silicone extrusions for implantable applications, long-term implantable applications like pacing leads or heart pumps that are used in class 3 medical devices.
Yeah, it's interesting with the onset of the COVID and all the vaccination applications, the biopharma processing tubing has really kind of played a center stage role. Simedex was not founded early enough to really jump in and take advantage of that wave of tubing that's required that you would see from some of the other major players in the marketplace. Names like Saint-Gobain, for example, or Freudenberg or Trelleborg would all be companies out there that were very active in the biopharm processing activity. But certainly from a volume of product, the raw material suppliers would have more definite metrics on that. But if you think about the poundage of silicone that is used specifically for conduit or fluid handling, peristaltic pump applications, that by far and away is the highest volume of silicone that is used in this segment of the market. As far as getting into the other question that you asked, short-term versus long-term, it's very common to see applications such as feeding tubes or wound drainage catheters, and specifically Foley catheters or urinary catheters that really drive a lot of the volume in that segment of the market, where if you're looking at class 3 devices, long-term implantable type products, you of course see insulation for pacing leads and neurostimulators, hydrocephalic shunts or glaucoma shunts for drainage in the body, hemodialysis catheters, peritoneal dialysis catheters, vascular access catheters for people suffering that need chemotherapy or immunotherapy. Those are just a few of the more commonly used applications that you would see that break down the market. Of course, in the body, when you're putting things in the body, the push in industry has been to go smaller and to go smaller for faster healing of wounds in injection sites and things. So poundage-wise, implants specifically are being driven to be smaller and smaller, and as a result, they're not using as much of the silicone raw materials. But that said, volume-wise in footage, there are applications that are commonly used, such as pacing leads, that do drive a lot of volume. But at the same time, there's also applications that the cardiac rhythm companies are coming out with leadless pacemakers that reduce the need of having those leads. So you have some things that are kind of balancing themselves out in the industry.
On the class 3 devices, that's kind of a different ball game altogether. The materials, the cost of the materials, the insurance policies, and on all the things that go with it. Can that be a challenge for a smaller company when you're competing maybe to some of the large companies that you mentioned earlier? Because the material is a big part of the cost of the extrusion, right? How does that play?
Yeah, it's interesting. That's an interesting question, simply because if you think about the extrusion process, you start with a standard, let's say a 2.5-inch extruder. There's different barrel sizes, but you have to charge that barrel. So before you even start trying to center a tool, hit a dimensional size, you've got $1,000 investment because you need 4 pounds of rubber to fill up the barrel. So, I mean, just whip out $1,000 bill to get started.
Yeah.
So knowing that, and knowing as a small startup company, we're not getting the negotiated pricing advantages that you would have of a larger company. Already we're starting with a larger investment in that raw material. So we use predominantly 1-inch diameter extruders for our implant applications, so that we can save on that initial cost with the benefit of a smaller barrel fill.
Yeah.
And so that's one area that we've tried to be competitive, or allow us to take that disadvantage and be faster at the the filling up of a smaller extruder to getting product coming out the end. So,
right. Okay. For the implantable applications, are there often antimicrobial additives that are blended with the silicone formulation to inhibit a microbial biofilm from forming on the surface of the implantable medical device?
right. Yeah. The most common additive are silver-based antimicrobials, and there's a number of versions that have come out in the marketplace over the past few years. Additionally, if the silver is not providing the antimicrobial properties that one's looking for, there's other companies that do secondary processing in batch processing of surface modifications, where they would add their own version of antimicrobial to prevent the formation of biofilm. Yes.
Gotcha. So it's a very thin, because silver is so expensive, it's probably a very, very thin wall on the outer surface.
That's correct. Yeah, it's certainly in certainly microscopic scale is what that's
Yeah.
measured at. So,
Okay.
yeah.
Interesting. On your website, you trademark a term called shapeshift technology. Walk our listeners through what shapeshift technology is and how it can be applied to certain medical device applications.
Yeah, so in shapeshift technology, we're talking about a transitional extrusion. So the idea of converting from one configuration to another in the midst of the extrusion process. Ultimately, what you're trying to accomplish is the reduction of labor in an assembly process. So a great example of that would be, let's say, a Jackson Pratt wound drain. And I could, for those of you on video, I could hold up a cross section. You can kind of see a transitional image here on the screen.
Yeah.
But we start from an ID-OD type configuration, and then we convert in that flat wound drain configuration to an oval configuration. So the idea in the extrusion process, if you can imagine starting, taking that ID-OD tube and splitting that circle at 12 o'clock and 6 o'clock, and as you are making the tubing, that circle will remain intact, but then on axes opposite each other, that axis will slide open to create that oval or oblong configuration that you need for the drain portion, and then actuate back in to provide that. So you're going in and out or back and forth to create that, and thereby you don't have any secondary bonding operation of a flat extrusion to a tube, or even some molded part that is going to be providing that transition. So the elimination of additional molding, tooling required, and the additional labor involved with doing the adhesive bonding step. So that, yes, shape-shifting technology is essentially a reduction in labor.
Okay.
Is what we're shooting for.
I saw a drawing once of that, a similar catheter to the shapeshift technology. I saw a drawing once, and I said, there's no way you can extrude this. It's got to be butt welded together. This is impossible. But obviously I was wrong. So that's very interesting technology.
Yeah, the idea of, you see in a lot of this technology, you hear about bump tubing. That's talked about a lot, which is also something that is considered, a transitional tube. But the mechanism to create a bump tube is relatively straightforward. You can change the speed of your puller wheel on the extruder and neck it down, or slow it down or speed up the extrusion line to draw it down. And of course, you're going to see a shrinking of the ID and the OD simultaneously in that sort of a situation. Maybe you have a catheter that you're trying to develop where you want a smaller distal end for the delivery, or in the anatomy where it's going to be going into the body. But along with that technology, or kind of doing the same thing, what if you want to retain the outer diameter, have that consistent, and change the inner diameter, or vice versa? That can be accomplished by the movement of the mandrel, or the pin in the ID, of course, pin forward versus pin back relative to a flush setup. As you've seen through the different setups that you've done over the time, that you will also get a fluctuation. Not as dramatic as a bump tube, so to speak, but nonetheless, you still, with servo drives and electronic controls, you can be very, very precise with those mandrel movements to give you that difference in dimensions.
Very interesting. Paul, from a micro extrusion standpoint, I saw on your website that you can extrude some very miniature silicone tubing. Tell us about your capabilities for extruding micro extrusions.
Yeah, Steve. Well, as I mentioned in talking about implantable tubing and trying to save money with raw materials, we've gone to a smaller barrel size on the extruder. But that precise control in the delivery of material has also allowed us the opportunity to more finitely control these micro tubes. So we are in production now on tubing with the dimensions of 3/1000ths of an inch by 9/1000ths of an inch. So, and that's something that we can do quite commonly. Of course, the handling of product like that is quite challenging because it's like you're dealing with your hair at this point in time, and being able to inspect it and all the secondary processing and packaging presents its own set of challenges. But nonetheless, it's something that we're very proud of the work that the engineering staff has done at Simedex to make that concept a reality.
Easy with the hair comments, please. But related to that, that such a tiny tube from a very soft material, and maybe the tackiness associated with the soft material, that's got to be extremely challenging.
It is indeed, but that's again fighting probably one of the biggest things we fight is static electricity. So using some your anti-static bars in the handling of things really helps in the management of and controlling particulate as well.
Yeah.
So
one other topic related that I noticed on your website, you talk about formed tubing, and I'm familiar with formed tubing on the thermoplastic end, where you take an extruded tube and put it in a mold or some kind of setup and put it in an oven for a certain amount of time, and it sets. Tell us, I've never seen it for silicone extrusion. Tell us a little bit about that formed silicone tubing technology that you have.
Right. Well, we were challenged by a customer to make a tube that's basically in the shape of a sine wave, where it undulates up and down. And this is an example of essentially taking advantage of the green strength that the silicone material possesses. So traditionally, in making a formed tube, you would pull out the extrudate green and lay it into a form, let's say an aluminum plate, or with the particular shape you're looking for, like a machined trough, if you can imagine that with that shape. You can see that done with applications such as the pigtail urinary catheters or the curlicues on a peritoneal dialysis catheter prior to the holes being punched at the proximal and distal ends of those products. In this instance, a client approached us, and they were using polyurethane material for an insulation for a neurostim device, and they wanted to go with silicone for greater patient comfort, because the silicone is softer and more pliable as the gold standard of implantable biomaterials. And so the method of making the polyurethane, of course, was to take a piece of polyurethane tubing, wrap it around pins, and then heat that up to the softening point, and then pull it out of the oven, and it would retain that set. So we have developed a process to make or manufacture the shape where we extrude it green into that form, and then thereby cure it in the oven or vulcanize it, and it retains that set without the real challenges, of course, being able to manage the curves without kinking the tubing and making the lumen close up upon itself through the sharp geometry that the clients are asking for.
You talked about the customer maybe tried the polyurethane first, and through the years there's always talk about silicone replacements with polyurethane and maybe some TPEs. Polyurethane is a TPE, but you know what I mean. What can you say? Is that true? Has then over the years been silicone been replaced with thermoplastics, soft? thermoplastics?
It all comes down to cost. You grab silicone, you will go towards using silicone for specific reasons, whether it's the temperature range, the biocompatibility, the various physical properties that silicone has. But the cost is always the driver. That's why if you look at drug delivery systems that on IV sets, at a hospital, you're connected to an IV. The majority of that tubing is PVC, except the working part is silicone. Because silicone can withstand that peristaltic application in those types of systems, for example. So cost is why people look at replacements such as a TPE, but there are certainly instances where you can't beat silicone.
Yeah.
And there certainly seems to be a market for us. We seem to the phone still rings at my end, even though TPEs exist out there. I'm happy to say.
Yeah.
So
no, I mean, it's the same thing in some ways in the PVC. People have bbeen talking about PVC replacements for years. And I remember Larry Johnson from Foster giving a talk a few years ago. He's been asked to look at different alternative materials to PVC. And he said, not one time has a project converted from PVC to an alternative. I know that might have changed by now, but I thought that was an interesting comment by Larry.
Indeed. Agreed.
Paul, silicone tubing, it's inherently flexible. And what comes with that often is a tackiness on the surface. And that could be a disadvantage in certain applications. In the thermoplastic world, when we have tacky materials, low durometer materials like a polyurethane or a 25D, 30D P-backs, those base polymers can be blended with lubricious additives to reduce the tack. In a silicone thermoset type application, are there additives that can be blended with the silicone formulation? Or are there processes like you talked about earlier with the silver that can be done in line during the extrusion process or as a post process to reduce the tackiness of the tubing, the surface of the tubing?
Yeah, there's not, it's an interesting question, Steve. There are different technologies, certainly for the treatment of the surface to reduce friction. And they're typically done in a secondary process. Parylene is commonly done, for example, or different siloxane treatments, where in a sense, you want to take this atomized silica and attack any free radicals that exist on the surface. And once those free radicals are then occupied, that gives you a much lower coefficient of friction. Okay. But in terms of doing something online during the manufacturing process, one of the things that you can do is you can add geometry. I mean, in most cases, you see in specifications that we receive, a desire for a smooth surface. There may be an SPI microfinish called out or something that we would polish a die to. But imagine using a wire EDM or something to rough up the surface of the die or to make striations. Mm-hmm. Now, you're going to have visual flaws where you would actually see die lines in a situation like that. But at the same token, if the outside surface is, if you can imagine a star configuration, mm-hmm. then you're going to have less surface area touching and thereby less surface frictional forces on the surface of the tubing. Right. So treatment of the die is the most obvious way to do something in a continual fashion while you're doing it online.
Right. So instead of adding something, you're reducing the surface area that the catheter or the tubing would come into contact with a mating device.
That's correct.
Sense. Okay, great. Paul, this has been an excellent conversation. We really appreciate you joining us today. We'll hope to have you back sometime soon.
I welcome for the chance to speak with you again, Steve. Appreciate the opportunity.
Thanks so much.
Thank you for listening to Medex, the Medical Extrusion Podcast, presented by US Extruders. Please subscribe to make sure you're getting the latest episodes. All links are available in the show notes.